Okay, good morning, everyone. So we will start soon. I will share screen. Okay, so good morning, everyone. This was the last slide of the previous class. So this gives that result concerning recurrence or transience of the birth-death Markov chain on 0, 1, 2, etc., with 0 as absorbing boundary. So you observe that this process is not recurrent. All non-zero states are transient, and only the 0 being the absorbing state is a recurrent state. All right. So we will go to the next thing. We will consider birth-death Markov chain with one reflecting boundary. And so once again, the state space is taken to be 0, 1, 2, etc. with 0 being at least partially reflecting boundary. So recall what is meant by partially reflecting is that, see, if it is at 0, if it is fully reflecting, at the next stage it will come to 1. In this case, it will come to 1 only with probability P0, which is strictly greater than 0. If P0, little p0 is equal to 1, then the boundary 0 is fully reflecting. We have seen that. So with probability 1 minus p0, in the next step, it can stay at 0. And afterwards, it can come out again. Okay. And for I greater than or equal to 1, it is just like the normal birth-death Markov chain. And with unrestricted. Capital P sub I plus 1 is Pi. Capital P I sub I minus 1 is Qi. And Pii is Ri. This Pi and Qi are strictly positive. Ri is greater than or equal to 0. Of course, all these three things together should sum up to 1 for every I. So Ri can be expressed as 1 minus Pi plus Qi. All these things you know already. Okay. Note it down if you want to. So you can easily verify that the state 0 is accessible from any y greater than or equal to 1. That is, from any state which is greater than or equal to 1, you can reach 0 with positive probability in finite number of steps. And similarly, from 0, you can come to any y in finite number of steps with positive probability. Consequently, this Markov chain is irreducible. All these things because we are assuming that this little p0 is strictly greater than 0. If little p0 is equal to 0, then it reduces the previous case. In this case, the chain is absorbing that with 0 as an absorbing boundary. All right. Now, to proceed further, note that the argument that we used in the case of unrestricted birth-death Markov chain.
Sir, is it the first slide of today?
First slide is to this thing back. Please try to come as early as possible. This is the first slide for today. Please note it.
Okay, sir. Can you go to the next slide?
That's what I have done.
Okay, sir.
So the argument we have used in the case of unrestricted birth-death Markov chain for computing the probability of reaching zero in finite time, starting from an y which is strictly positive. That is valid in this case. That is, we have taken in that case C, capital C strictly less than D, and probability of reaching C from any y between C and D. And then later on we had let D go to infinity and so on. So that argument is, it just goes through, because in this case, this is all has to happen before reaching zero, or just before reaching zero. So that is valid. Yeah, I'll go to it. Please note it down if you want to, so that I can go to the next slide. Okay. So in that argument, in the case of unrestricted birth-death chain, take C equal to 0 in what we had denoted as by the spade suit. Let me see if I can go back to that, since it is in the same notes. Yeah. So in this expression, we take C equal to 0. So the summation here will be from sort of 1 to D minus 1, and then later on we will let D go to infinity. And consequently, this is what, say here, if we put capital C equal to 0, so that what we will get is the corresponding to this. Just refer back to that. Yeah. So if you do that, so this is time just written down the corresponding expression for that psi, what we had in that context called as psi y, and this is equal to this. Oh, there is an unnecessary comma here. This comma can be deleted. Where this lambda x is, since here C is equal to 1, I have written it again. Q1, Q2, Qx over P1, P2, Px for every x, 1, 2, etc. Note it down. So rho y0 is equal to this expression. The y occurs here. Please note it down. So, okay. So consequently, we get, so if this were to be 1, this guy, as D goes to infinity, should go to infinity. That's what I have written. Just like as we had seen earlier. So rho y0 is equal to 1 for all y greater than or equal to 1, if and only if this series diverges. These are all non-negative terms, rather strictly positive terms, because Qis and Pis are strictly positive. Now, by an argument again similar to what we had done earlier, which I think that equation we had denoted as star, you can see that we will get rho 0, 0. See, in that case, we had expressed rho YY in terms of our rho CC in terms of rho C, y plus 1 to y plus rho y minus 1 to y and so on. Here 0 to the left of 0 there is nothing. So this is the probability that the process reaches 0 in very first step. That is, it doesn't go out of 0 in first step. And when it goes out, it is in state 1. Then it is a probability of coming back to 0, from rho, that is starting from 1 coming to 0 in finite time, and that is this probability. So recurrence would depend on, say for example, the state 0. See, we have seen that this Markov chain is irreducible. So if we show that there is one state which is recurrent, the entire Markov chain is recurrent. So we should have rho 0, 0 equal to 1. Now, however, since P0 is strictly positive, 1 minus P0 is also strictly positive. Consequently, this quantity, since P0 is strictly positive, this quantity will become 1 if and only if this guy is 1. That is, rho 1, 0 is 1. Please note it down. Yeah, so that is what I mentioned in words, it is given here. Since P0 is strictly positive, rho 0, 0 is equal to 1 if and only if rho 1, 0 is 1. And since the Markov chain is irreducible, we have the following result. So let Xn be birth-death Markov chain on the state space 0, 1, 2, etc. And 0 is at least partially reflected. Then P sub 0 is strictly greater than 0. Then the first conclusion is Xn is irreducible. And the Markov chain Xn is recurrent if and only if rho y0 is equal to 1 for all y greater than or equal to 0. That is if and only if rho 0, 0 is equal to 1. That is if and only if rho 1, 0 equal to 1. Moreover, the criteria in terms of coefficients is the process is Xn is recurrent if and only if this series diverges. Of course, if this series happens to converge, then the process will be transient. Please note it down. Okay. So now we will prove another result, which is a kind of general result, not necessarily concerning birth-death Markov chains. So this result says, if you take a Markov chain on a finite state space, then there is at least one recurrent state. So in particular, an irreducible Markov chain on a finite state space is recurrent. I mean, intuitively, this result is not, I mean, you can easily guess this should be the case. See, we have seen that if you have a transient state, I mean, if all the states are, if there is a transient state, the Markov chain can come to that transient state only finitely many times. Okay. So if there are only finite number of states, since the state space is finite, then there will be only finitely many states. So from each state going to some other transient state, then it also can be possible only for a finitely many times. So because there is not much freedom there, no, since it is a finite state space, the Markov chain has to come back again and again to at least one state. So this result is easily guessable. Of course, one has to supply an argument.
So, sir, I have a question. So, an irreducible Markov chain is either recurrent or transient, right?
An irreducible Markov chain, well, if it is, there is a transient.
No, means if an irreducible Markov chain has a recurrent state, then all states are recurrent.
Yeah, if a Markov chain is irreducible, and if there is a transient state, it is a transient.
And if there is a recurrent state, all states are recurrent.
If it is irreducible.
Yeah. Given that the Markov chain is irreducible,
yes,
either all states are transient or all states are recurrent.
Yes.
Okay, fine.
But this first part of the theorem does not concern irreducible Markov chain.
No. First part is simply okay. Because there are only finitely many states, and if
So the thing is, once you have this result, this one is an immediate consequence.
Yeah. Because there is a recurrent state, so all the states must be recurrent.
Yes.
Because it is irreducible. Okay, fine.
Correct. Okay, now let us look at the proof. Please note it down if you want. So let Xn be a Markov chain on a finite state space, yes, and let capital P denote its transition probability matrix. Okay. Suppose all the states are transient. Well, we know that since the P is a transition probability matrix, it is a stochastic matrix. So take P super bracket n. So that is the nth n state transition probability matrix, which we have seen earlier that it is just P power n, the matrix product. You can verify easily that this Pn is also a stochastic matrix. So stochastic matrix means every row sum should be equal to 1. That's what. Yeah, please copy down if you want. Consequently, we have the row sum equal to 1. So for any x in the state space S and any n, if you take P super n xy and sum over the y's, so it is the xth row, x row corresponding to x, and the column corresponding, I mean this thing, all the y's in the column. And all the column vectors along that row. Because starting from x, it has to go to some y or other in the state space. So this is equal to 1 for all n. So as a function of n, the right hand side here, that is a constant. Therefore, it is also equal to limit n going to infinity of this quantity. Right? Is this clear? It's a self-evident kind of truth. Otherwise, yeah. So why the reason for saying this is for all n. And this is a constant. So limit of this guy is also 1 for every x. And here we have finite summation, that is a sum over only finitely many terms. So there is no problem about interchanging the summation and the limit. So that is what I am saying here. So no problem about interchanging the limit and summation. Consequently, sum over y varying over s, limit n going to infinity of Pn xy, P super n. So that is for each y, you take the limit here. So this is equal to 1. Please note it down if you want. So now we will get a contradiction to this statement. This equation, 1 equal to this one. So we'll go to the next slide. So recall our g. G is the gxy. G is a function of 2 variables. So starting from x, gxy denotes the expected number of visits to y. So by definition of
So sir, here n of y means number of visits to state y, right?
Yeah. Please, this is all old notation.
Okay, fine.
So this is expectation of ny given x0 equal to little x. And that this is the notation for that. You remember that. So E sub x of ny. So ny is the number of visits to state y. So that is basically can be written as summation n going from 1 to infinity I sub y xn. So this is an indicator function of the singleton set y. You know that. So this guy I sub y xn equal to 1 if xn is equal to y, and it is 0 if xn is not equal to y. So this summation precisely counts the number of visits to y. So you know that for every fixed y, ny is a random variable. So now this random variable ny has been written in the form of a sequence of random variables, each of which takes the value either 0 or 1. And it is equal to 1 when xn equal to y. That's what this is. We have this argument we have seen even earlier. And here all the quantities here are non-negative. So interchange of this summation and expectation is okay. So from your basic probability course, you know that expectation of an indicator of a set, that random variable, gives the probability of that set. So E sub x, I sub y xn is precisely probability that xn equal to y given x0 is equal to x. Okay, this x is sort of superfluous here. And this precisely is. I mean, this x, and since this x is there, here the x is there, this is sort of superfluous. The probability xn equal to 0 given x0 30. And by definition of the n state transition probability, this quantity is precisely the probability of reaching y in n steps starting from x. So this is basically the crucial part of the argument. Please note it down, and also please go through it. Just simple proof, but the what I had mentioned as the intuitive way of arriving at that result, it is basically contained in this thing. Making that argument rigorous, that intuition rigorous, using the results which we have already proved.
So now what we can do is we can sum the expression in the previous slide.
Just next step we will go, you will see.
Yeah.
Yeah, I think you have got it. We'll sum it over x or something like that. X or y, as the case may be. And this result holds, note that for every x and y in S. So as he has pointed out, once we come to this thing, the next steps are guessable easy. Since each y is transient, because we are saying that suppose we are proving this thing by contradiction. So we want to prove that there exists at least one recurrent state. So that the negation of that is supposing all the states are transient. Yeah. So since each y is transient, by an earlier result, the expected number of visits to y is finite for every starting point x. And since each y is transient, this holds for each y in S. So now, again, go back to the way we have written gxy and all that. Gxy is nothing but summation over n going from 1 to infinity, p super n xy. So since this happens for x and y, every x and every y, this also is true for every x and every y, because it's the same. So since for every xy this happens, since this convergence takes place, this terms as n goes to infinity, that converges to 0. That's the crux. So as the series converges, we get limit n going to infinity, p super n xy is 0 for all x and y in the state space. So consequently, as S is a finite set, it follows. So each of this limit is 0. So now you sum over y. So it's a finite sum. So this also equal to 0. And earlier we have got that sum is equal to 1 for all x. So now we are getting for each x, this sum is equal to 0. So this is a contradiction. So there is at least one recurrent state. So contradiction, because of the contradiction, now we know that not all states can be transient. So there will be at least one recurrent state. So the second assertion is now immediate from the first assertion. So this completes the proof. So this is a fairly important and useful also result because this concerns general Markov chain on, a finite state space. In many applications oriented things, you might be seeing finite state spaces. Because our capacity is only finite, human capacity. The other things are basically, these are considered as a kind of what happens in the limiting case and things like that. So a result concerning purely finite state space, this is, I think, the kind of first kind of result we have seen. So now we had been seeing birth-death Markov chains, unrestricted Markov chain, then Markov chain with on that infinite state space, namely 0, 1, 2, etc., with 0 as an absorbing boundary. And then we saw today in the morning the same state space, namely 0, 1, 2, etc., with 0 as at least a partially reflecting boundary. So one of the things which we had left out was, again, an important case is that a birth-death Markov chain with 2 reflecting boundaries. So easy consequences. Any birth-death Markov chain with 2 reflecting boundaries is recurrent because it's a birth-death Markov chain. And if you have reflecting boundaries, the Markov chain is irreducible. That you can easily check. And that immediately tells about an important Markov chain, which also is of historic significance. The Ehrenfest-Earn model is irreducible and recurrent. So this is the last slide for today. So if you want me to go back to any of the slides, I will do it. Or any questions if you have?
So which book are you following?
I am not following really any single book. Hoyle-Portenstone stochastic process is some kind of a guide. But some things I'll be, see, these are, I might have consulted in the past and all that. Some of other books also. So I am not following any single book.
At least can you suggest a book where the notation is same?
That also I cannot do. See, Hoyle-Portenstone it gives quite a few materials. And that is a kind of follow as a.
No, because whatever book I have tried to refer have notation different from
Notation
yours.
will be different because since one forms one's own notation. Many teachers, I suppose, may be using different, several books.
I think basically the notes are self-sufficient.
Yes. So notes have they are consistent notation.
Yeah, exactly. Yeah.
Say, especially since it is an optional course, one takes the liberty of following quite a few books. And also, since for this thing, it is enough to take 2 classes per week, but I'm taking 3 so that I can go at a slower pace. And also, since the slides are already prepared, one doesn't spend time writing on the board, erasing, etc., etc.
Yeah, means I think in Blackboard teaching it would take more time.
Yeah. I mean, some of the things that is what one does in about 1 hour, 10 minutes, and things like that. We are able to do it in about 35 to 40 minutes. Of course, I also try to give time for you to copy down if you want to.
So do you make these slides in Beamer?
Yes.
Okay. So what is the latex symbols for these? I mean, dagger, double dagger, which you use in your slides?
It's all, say, I use that this thing editor TechMaker.
Okay.
And there it that one this thing one particular key I press, it drops down various symbols.
Okay. Okay.
Yeah.
Yeah, because there are various symbols like heart, spade, all these things are there.
Yeah. Well, I mean, there may be some other editor which may give even more symbols. Huh?
Okay.
Okay, so we will stop here for the day. Stop sharing. And by the way, I find it only very few students are attending. Okay. Of course, I presume they are all keeping track. All right, I will end the session now. And okay, take care. We will meet Monday.